Okay, in our last section, we learned what a derivative was. A derivative is an instantaneous rate of change. We learned how to calculate that derivative using something called the difference quotient, right? We saw that the derivative of a function we can find by taking the limit as h approaches 0 of this difference quotient, right? F of x plus h minus f of x all over h. And the idea of this is that we're finding a rate of change and we're letting that interval for my rate of change approach 0 so that we can find that instantaneous rate of change. But as we saw with your homework that you did in 1.4 and also with the examples that we went through, that gets using this difference quotient gets pretty tedious. There's a lot of just expansion and then simplifying, right? It ends up being a lot of busy work. So this chapter is all about, can we find shortcuts to differentiation? Are there shortcuts I can use when I'm calculating my derivatives? So let's start with a really basic type of function. Let's start with just a linear function. So y equals mx plus b. This is how we're used to seeing linear functions in slope-intercept form. What would the derivative of a linear function be? Now, I could go through the work and use my difference quotient here in order to figure this out, right? And I would do m of x plus h plus b minus mx plus b, right? Your function with x plus h plugged in minus your function all over h. Now, I could do it that way, and I can work through it, but I can also think through this logically. What do we know about linear functions? Linear functions have a constant rate of change. What do we call that constant rate of change? The slope. Well, what do derivatives find? A derivative is all about what's the rate of change at a point. Well, if my rate of change is always constant, then it doesn't matter what x value I pick, the rate of change will always be the same. What is that rate of change? The slope. So what's my derivative of a linear function? It's just whatever the slope is. So there's a nice shortcut for linear functions. I'll write that out. If f of x is a linear function, then f prime of x is just equal to the slope. Okay, well, let's keep going. What if your function is a constant? What does that mean? That means it's always the same no matter what x is. It's always just one y value. It's a horizontal line. What would my derivative be? Well, remember, a derivative measures how the y value changes as the x value changes. Well, is this y value changing? No, it's not changing at all. There is no change. So if there is no change, what's my derivative? 0. So this is another shortcut we can use if we're working with just a constant function. The derivative of any constant function is 0. So we now have some derivative shortcuts for linear functions and for constant functions, but let's try and get a little bit more complex. And we're going to start with power functions. Let's say my function is a power function. What is a power function? A power function is when you have x raised to a power. Okay? We're going to use k to represent just that constant power. So k is a constant in this case. So if I have a power function, what's my derivative? Well, with power functions, it's pretty nice because we could use the difference quotient for all of them, but we don't want to have to use the difference quotient every single time just because it's time consuming. Can we find a shortcut? Well, we actually already have one piece of our puzzle, and that's this piece. What if I have x to the first? Well, what is x to the first? X to the first is just x, but this still counts as a power function because it's being raised to the first power. So it still counts as a power function. Well, since this is a linear function, we know what the derivative is going to be. The derivative is just going to be the slope. I don't see a slope in front of my x. So what number can I put there? I can just put a 1 there. So it turns out my slope is just 1. My derivative is just 1. Okay, so there's one piece of the puzzle. But to get my other pieces, I do have to use the difference quotient. Let's look at x squared. What's the derivative when I have x squared? Well, like I said, the only way I know how to find this derivative is by using the difference quotient. So that's what I'll do over here. I'm going to do x plus h squared minus x squared all over h. I'll go ahead and span x plus h squared to get x squared plus 2x plus 2xh plus h squared minus x squared. And notice I have an x squared minus an x squared, so those terms will just equal 0. And every term that I'm left with, both the terms that I'm left with both have an h in it. So I can factor out an h out of my numerator. And now that h that I factored out cancels out with the h in the denominator, and I'm left with this limit as h approaches 0 of 2x plus h. Since I've now eliminated the discontinuity, I can plug in 0 for h, and I'm left with 2x. So here's the next piece of my puzzle. If I have x squared, then I get the derivative 2x. Okay, now here's the last piece. Let's do x cubed. Now, if I actually walked through the process of x cubed, it would take a good amount of time. So to save us time, I'm just going to tell you what the derivative is for x cubed. Your derivative ends up being 3x squared. So now that we have these three derivatives, hopefully you can start seeing a pattern of what happens when I take the derivative of a power function. Notice how you end up multiplying by what the original exponent was in the derivative. And then notice how the new exponent is just one less than the previous exponent. In this derivative, in the derivative of x squared, I get 2x. Well, that's 2x to the first, and so my new exponent is one less than what it was before. Even in the derivative of x to the first, when I take the derivative, I get 1, and if I wanted to, I could put an x to the 0 there. Because what's x to the 0 equal to? It's just equal to 1. And we can see how that exponent is 1 less than my starting exponent. So, because this follows a pattern, I now can come up with a derivative rule for power functions. If your function is a power function, then the derivative of it is you multiply by what your original exponent was, and then you decrease the exponent by 1. So I get kx to the k minus 1. And this is known as the power rule for derivatives. So now we have a nice shortcut rule for power functions. But we're still pretty limited, right? We're still limited to linear functions, constant functions, and power functions that are in this specific form, x to a power. So consider this function. Well, if we look inside of it, we can see, oh, hey, there's a power function. Oh, hey, there's a constant function. And this counts as a linear function, or you can think of it as a power function, right? I could also put a power of 1 here. I could also put a power of 1 here and think of it as a power function. But there's a lot more going on, right? This isn't a simple power function, it's a quadratic function. So I can't use any of the rules that I have. But there's gotta be a simpler way to do it if I know the derivatives of each of these pieces, right? Well, let me introduce you to a couple more derivative rules that are really, really helpful. The first one we're going to look at is called the sum and difference rule. The sum and difference rule tells me that if I have two functions that are being added or subtracted together, and I want to take the derivative of them, if I try and put add and subtraction inside that difference quotient, it's going to get pretty complicated. Well, it turns out that it's as simple as just taking the derivative of each piece separately and then adding them together. So I can take the derivative of f, then take the derivative of g, and then add or subtract it. Well, why is that helpful? Well, if I come back to this, my example here, if I recognize this is linear and this is a constant function, I can just focus on the derivative of each of these pieces individually, and then when I'm done, put it all together as a derivative. And same with this term, is I can just focus on each term individually, and when I'm done, add them all together. When I'm done finding the derivatives, I can then add them all together. So that's the sum and difference rule. The next rule that I'm going to talk about is called the constant multiple rule. And this answers the question of, what do I do if I have a coefficient? What do I do if I have a number being multiplied by my function and I want to take the derivative? So what do I do if my function has a constant in front? Well, it turns out that that constant does not affect your derivative. You can just take the derivative of the function like normal and then multiply it by the constant. So once again, why is that important? Well, if I come up back here, my x squared term has a coefficient. What do I do with that coefficient? Well, that constant multiple rule tells me, hey, I can just take the derivative of x squared and then multiply it by 3. And that's the constant multiple rule. So with those two rules, if I come back to my example problem of 3x squared plus 5x plus 9, the sum and difference rule tells me I can focus on each piece individually. What's the derivative of 9? Derivative of 9 is just 0 because it's a constant. What's the derivative of 5x? Since that's linear, the derivative is just whatever the slope is. So the derivative is just 5. What's the derivative of 3x squared? Well, I can ignore the constant and just focus on x squared. That's going to give me 2x, and then I can multiply by that coefficient. I can multiply by the constant. So I get 3 times 2x, which is 6x, plus 5, plus 0, but if it's a plus 0, I don't actually need to put it there. And that's my derivative. And that was so much easier than going through the difference quotient method, because I can just break it up into more simple parts that I know how to take the derivative of. Well, those are all the different derivative rules that we're going to talk about today. We'll get into some more starting in the next section, but I do want to talk about some special cases. What do I do with something like this? Well, it turns out if you're ever working with a root function, it counts as a power function. I can rewrite this as x to the 1/2. And guess what? The power rule still works even if your exponent is a fraction. So what would my derivative be? My derivative would just be, I would bring down the exponent and multiply it, and then subtract 1 from the exponent. Reduce that exponent by 1. Well, what's 1/2 minus 1? I get negative 1/2. And that would be my derivative. Well, speaking of negative exponents, what about this example? What if you have something like this? What if you have a power function in the denominator? I can interpret this as negative exponents. So I could rewrite this as x to the negative 2. Anytime you see a power function in the denominator, you can rewrite it as a negative exponent. And so, and guess what? The power rule still works with negative exponent. So what would my derivative be? I would multiply by the original exponent and reduce that exponent by 1. You do have to be careful here, though, because if I reduce a negative number, it becomes more negative. So I end up with negative 2x to the negative 3. So the power rule still works for fractions and negative exponents. And I'll just remind you, just with the fraction exponents, the way that it works, so this is just a review from college algebra, but if you have x to a power, but that's also being rooted, how do you write that as an exponent? You write that the power that it's being raised to is just your numerator, and your denominator is whatever the root is. So that's just a good reminder of how you write fraction exponents. Well, that's it for our simple derivative rules. Go ahead and get started on the homework, and I'll be going over a couple of problems from the homework in my examples video, so you're welcome to tune into that if you have more questions. Good luck, guys.